Continue this investigation to Ito's lemma, and I'm just gonna apply it to a bunch of things. So here we have the two forms, right? I'm gonna apply whichever I feel like, or whichever is easier. And to be clear, this is just a partial derivative, nothing fancy. I just wrote it in a more compact notation, and this is the second derivative with respect to x. Okay, so let's start. F equals t. Then we're gonna have that let's apply this one. Okay, and that's just gonna be f equals t df. We apply the first one. All the x derivatives are 0, so it's just gonna be 1 times dt. Okay, pretty obvious, right? So notice that when we do df is just equal to d of t, which equals d of t. So this works out. You can somewhat manipulate it as if it's the usual differential. Okay, but we're gonna put that aside for now. Let's hide it over here. Okay, this is the first one. Second, d f equals wt. Then df, oh, we don't need to put it aside. It's w t. Okay, let's work it out through Ito's lemma. Okay, if we look here, this term is 0. This oh, let me be clear, let me be very clear with what I mean by this. Ft is going to be ft wt equal wt, so defined as wt. Okay, right? Now clearly dt of f, where's to be clear, okay, so this is how you do it. There's a thing that might be unclear here. When we take our partial derivatives, we are not considering this kind of thing here where t is explicit. When we're taking our partial derivatives, let's put it over here. What we're actually considering is a function of two variables where nothing is weird or sketchy. Here there's weird and sketchy things. This is a stochastic process. This, when we write like this is just a function f of dx. In this case, we want the function f of dx equals to x. Okay, so when we apply this to f of t wt, when we evaluate this, this is just basically, this is just the definition. It's what we define it as. And when we evaluate this, we are gonna get this. Okay, that's why this, what we're saying, is kind of mostly well defined. We're gonna hide this again. Let's put this to the side. Okay, so I mean, what we'd like to say is obviously df is d of wt, which is just d of wt. That's one way. But through Ito's lemma, what we're gonna say is actually that df is gonna be, so this, it's actually the function that's here, right? So with respect to time, the derivative is 0. With respect to x, the derivative is just 1 times the xt. Okay, where xt is gonna be wt, because in this case here it is, it didn't have to be plus 0 because the second derivative is just 0. So we obtain df dwt. Okay, let's continue. What if f equals wt? The naive way is df is just equal to dwt squared. Well, why is this bad? Well, because this is not in the canonical form. We always want to express something as like basically linear combination a dt b dwt, right? This is what we always want, but this is not in that form. Okay, always usually wt, because wt is just it's the main stochastic process that we're interested in when we do Ito calculus. It's the one we know how to handle, or that we pretend to understand at least. So df equals this. But let's not write it like this. So here f of tx is going to be equal to x squared. Okay, and so it's going to be 0 plus this time derivative, space derivative, or x derivative is we can even write it like this and then substitute later on plus 1/2 2 dx squared. Okay, so df is going to be 2x dx plus 1/2. So dx squared. Now we just do the usual x equals wt, and this is going to be equal to dwt plus dwt squared d2wt plus dt, because dwt squared is equal to 0. By the way, what this actually denotes is interesting. Just basically the variance of the Brownian motion is actually basically proportional to the beginning time, the final time minus the initial time. This is gonna basically represent the variance. But yeah, and I guess this is not exactly canonical form because dt appears first, so it's like 1 times dt plus dwt times dwt. Okay, and this is the canonical form. This is the drift part. This is going to be the drift coefficient. This is going to be the this is the diffusion coefficient. This is the drift coefficient, right? I think so. Okay. What's a big consequence of this? A big consequence. We can conclude from this that so d of f as here as a time dependency as an extra dependency here. So dt0 dw squared. So this of course is gonna, by definition, to this. This is actually gonna equal. This integral 0t dt plus. So the integral of this basically, of this differential, is gonna be equal to this integral and the integral of dwt times dwt. Okay, pretty cool. It's gonna say a square word, and it should be. It's fine. Nobody cares. Then we get this equality. Very, very good. Which also gives us. So let me finish computing this. So obviously, what's this integral? This is just t minus 0, so just t0, dwdt, dwt. Okay, which is pretty cool. So, and I should definitely stress this. So, and another way of representing this equation is that pwt squared equals dt, sorry, dwt, dwt. Okay, I'm just taking this from here, and I'm taking this from here. This is just the same thing. So this is a pretty big deal. We're also saying that if we wanted to solve this differential equation, so if we wanted to basically solve this differential equation, the solution would basically end up being this. And we could do some shifting. We know this is true, right? We can do some shifting to obtain something very, very good as well. Very, very good. Oh, sorry, there's a minus. Okay, let's pass this here and this here, okay? We're gonna conclude. Or actually, let's just pass this here. Easier. Okay. This. Remember that this notation denotes an integral. We just have to add like an integral on both sides. Okay, so we can pass it to the other side. It's no problem. This is going to be equal to 2wt dwt. Okay. Now we're taking the integral. This means dwt squared minus w0 squared minus t is going to be equal to 2 times the integral of wt. Sorry, a little detail. This is an s. Okay. I think it's obvious why it should be an s, right? This variable is going to change through the integral. In this integral, t is going to be fixed, so the variable that's going to be changing is going to be this. Okay. Anyway, this is a big deal. Now we know how to do this integral. That's pretty great. Pretty great. Okay, so what's going to happen is that we're going to pass the 2 to the other side. We're going to divide by 2, okay? That's great. That's really, really good. So I was gonna do this one, but I might have messed up. I'm just gonna ignore it. I'm gonna ignore it. Because it's pretty easy. We did this. We just have to add whatever the integral of this is. So t cubed divided by 6. Whatever. Nobody cares. Let's do the exponential one. Okay. And then the and then the logarithm. Okay. If f of t wt is gonna be equal to what? It's gonna be equal to e of t and then wt. Is it minus or no? It's just alpha. Okay, so in other words, f of tx equals e of x alpha t x. Let's grab our friend over here. I much prefer this version, to be honest. At least I feel like I know what I'm doing. using it. Okay, this is gonna imply, so df gonna be equal to, okay, very hard differentiation. When we do the integral of the exponential, alpha e alpha t x plus dx sorry, something. It's gonna be e alpha t dx plus 1/2 of second derivative of this is gonna be 0 dx, pretty trivial, alpha e alpha t x plus e alpha t dx. Okay, so this is gonna be, I forgot the dt, sorry. There we go. Which is just gonna be alpha e alpha t, when we substitute x for wt, dt plus e alpha t dwt. Okay, this is gonna equal to e alpha t dwt. Okay, can we conclude anything cool from this? We kind of can, somewhat. Another way of expressing this is that we have a process. So this is going to be a solution of the differential equation alpha xt dt plus e alpha t dwt. Okay, that's relatively cool. Okay, I went to check if there was a certain integral that we could solve. And I'm back. I'm just gonna do one more integral and end it. As for this one, well, we can't say much more. I think we can say more, but not much more. I don't think we're gonna get anything clean out of this. Or I'd have to think more. Maybe it's possible to solve this. This is a differential equation, a stochastic differential equation. But anyway, okay. I'm gonna go just one more. If ft here wt is just going to be equal to logarithm of wt. Now what do we get? We're going to get that, sorry, dft is going to be equal to 0 plus 1 divided by wt, 1 divided by wt times, it's going to be dxt, so dwt, plus, here's going to be minus 1 divided by wt squared. Sorry, this is already the second derivative, times dx, so dwt squared. Okay, so this is just going to be equal to wt squared dt, this is dt, okay, plus 1 divided by wt dwt. Okay, now there's a big warning that I should give. I just noticed. Warning. Okay, let's make it big. Warning. So, in all these examples, so usually we have Usually we have that f equals f of x of t, right? As f of t x of t. But in all of these examples I have had x of t equal wt, and therefore dxt equals dwt. Usually harder. So usually more terms. Because usually we're gonna have that dx of t is gonna be equal to something mu dt plus t as plus sigma dwt. Okay, but here all of this was cut out basically. You don't have this extra annoying dt term, you don't have this mu term, you don't have this sigma term. That's all really simple. Okay, so careful. This can be not the usual. Well, it's arguable, but at least harder. At least it's easier. It's easier. Okay. Anyway, that's it. I'm gonna stop here.